Okay, so this week is all about data. Last week we looked at hardware, the physical device itself. But we're using it for that flow that we talked about a bunch of the first week, and it's going to keep coming back to it. Are raw facts, just the numbers with no context. Right? The number 4, don't even have a dollar sign on it to know that we're talking about money. Could be about any number of things. From data, information, which is useful data, is a common way to phrase that. We add some context, we make those raw facts useful. Then when we apply them, that's knowledge. And learning from that application, kind of looking back and reflecting, that's where wisdom. So that flow. An ancient need of humanity, and computers are just our modern tool for doing it. So we looked at the hardware, talked about a few of the pieces, took some machines apart last week, put them back together. How did those things, right, when we got to that CPU, that's just one solid chunk. It's inside a metal case, but if we broke it open, it's still one solid chunk inside there. It's a kind of clear purplish goo. It's soft, but squishy. If you find an old piece, you can cut open and see what they look like. That's what actually does it. It's just one piece there. How is that doing that? And you've probably heard that it's a bunch of switches. I'm going to erase this. We've talked about that before. We're going to talk about, that's really what we're looking at with informatics and IT in general. That flow and the tools we have to do it. So how does that start at? Or even if we go back to the old ones when we could actually physically see the switches themselves before today's transistors, which then eventually led to MOSFETs. We have one solid piece. We can see the little switches, and how do those on-off things relate to numbers? So on day one, I drew this a picture of a circuit, looks something like this. So if we have a open switch, I'll just draw 4 here. Then a closed switch. An open switch. And another closed switch. That's one way to represent 5. 0, 1, 0, 1 is how we would normally write that to indicate off and on. But I will, those are just symbols representing the state of that switch. Off and on is kind of relative. Some things actually come on when we take the electricity away. Actually, the screen is a great example. If you, not many cathode ray tubes left anymore. So most of us are sitting here staring at the LED screens, LED or OLED or something with individual control of each pixel. And exactly half of those pixels come on when we send it a 1, which would be flip the switch to the on label. And half of those pixels come on when we send it a 0, which is like if we compare it to the light switch on the wall, I think it was flipping the switch to the off position. Actually turns that on. That's done to optimize components. You'll have probably noticed that sometimes screens can take a lot of damage, but a little bit of damage in certain spots will destroy the whole thing. It's done to optimize it that way, and it consolidates the weak spots so that it's less likely to hit one of those weak spots. If most of the screen can handle damage, it's less likely that you're going to hit that one key spot. But half of the pixels come on with the 0 and half of them come on with the 1. So when we get into the advanced stuff, it's like that. So for our purposes today, I'm going to say 0 represents off and 1 represents on. And when I'm writing binary, I do leave the little flags off. Normally my 1s have serifs all over them because there's almost always vertical lines showing up. Don't need 1s blending into those as well. But for binary code, there's going to be lots of 1s. So I stick with the vertical lines there. But it's binary state machines. off and on, just talking about the switches. But when we start applying meaning here, that might not be the best words. So we just need any sort of binary states. True, false. It's a good combo. Up, down. High, low. This is what it would actually represent. We're talking about electrical voltages. So if we plotted it like voltage over time, we kind of set some threshold. It varies in most machines these days. It's 1.2 volts. We still see some 5 volt or 3.3 volts, especially in IoT devices where we're going to be powering something bigger. We're going to step it up. So we start with like slightly larger. We start with a 5 to step up to 110 volts instead of starting with a 1 to step up to 110 volts. But we just have this threshold, and our voltage is either going to be above or below that, high or low. So maybe at first it's down here, at some point it jumps up, back down, then up, and we'd represent that. Look at the time and 0, 1, 0, 1. So it's either below or above the average. Maybe or above or below that threshold we set. So above or below, there's lots of binary states we can use. Yes, no are some great ones. If we're doing something where we need to think about the logic, try different words. Try different binary states, because we know it's binary states. We have lots of binary combinations in the English language. So maybe a different set of words will help you make sense of what's going on there. And then that thing I said earlier about how there's arbitrary assignment. We decide what the symbols mean, and we can negate it back and forth for what's best for the circuit. So there's some technicalities when we get very advanced. We just kind of wanted to introduce it. So start with like, how do I know that means 5? Y'all, if you haven't seen it before, we are in full agreement that combination of switches represents a 5, just like we are this symbol right here that I drew here represents 5. 2 different ways of representing that thing. It's okay if I erase this. So just some preview. And I like to cover this here because the course where this is actually listed as a major learning objective is another one that everybody in School of IT has to take. And it's the Introduction to Logic course. And over the years, things keep getting added to that course. Like more and more course objectives learned. So that's the course where binary is officially on the list to learn, but there's so much in there, it just kind of blends into it. It just blends into the overwhelming flow of information that you push through the semester where you take that course. Or the 8 weeks where you take that course now. I don't think there's any 16-week versions of that course that are running. So a big flood of information, and sometimes it gets lost in there, but where you're heading in IT, you're going to be working with binary stuff. And I guess to start with, you've probably heard the phrase computers are machines that do math, or they do some sort of math. So it's all based off numbers. And that's kind of what we're looking at. And let's review something you probably haven't thought about since like 2nd or 3rd grade, wherever it shows up. And then we learned that and we never really break it down again. So let's say we had this number 748. Y'all remember way back in elementary school how we define what that number really means, how we know what those symbols represent? Well, first off, it's in base 10. That's just a convenient number for humans to work with. We have 10 fingers, so it's a good one. We can use any base. There's nothing special about 10. It's just convenient for people. Also using our fingers, base 60. Let me try into this camera. So 10, if we just hold our fingers up one at a time, I think y'all are probably familiar with that. Base 60, if on one of your hands, count the little ridges, touch your thumb to your ridges, and there's 12 there, so you can count to 12, count to 12 5 times, or count to, like a clock, count to 5 12 times to get the base 60. any numbers, there's nothing really special about what we base it on. The patterns still apply. And the base, we're basing everything off 10. So if we look at what this means, it really means we have 700s. I'm just going to write in this time. I'm just kind of jump ahead because I know I saw this way back in elementary school somewhere. We have 700s, plus we have 40 10s, plus we have 8 ones. And that's what that number really means. And the fact that it's based off 10 means we're going to use the same number for every one of those columns. So when we use, for a 3-digit number, we have 3 different columns. If that extended to a 50-digit number, we won't come up with 50 different values that every column's based on. So we base them all off 10. So 10 raised to some power. 10 raised to some power. Or 10 raised to some power. 1 is just a rule for mathematics. Any number raised to the 0 power is 1. So we put an exponent of 0 there. I always remember that as we have something, otherwise we would make 0 our big number, but we don't really have anything of that something we're writing down. So somewhere in between 0 and anything else is a 1. That's how I remember that rule. But any number raised to 0 power is 1. This one would just be 10 to the first power, 10 to the second power, 10 cubes, 1,000, 10 to the fourth, 10,000, and we just increase our powers of 10 going over. And like I said, there's nothing special about 10. We use any base. So on the transition to the one we're actually heading to, let's try base 6. Let's use 6 for a base. Just pick an intermediate spot. I guess one other note here, for base 10, we need 10 symbols, which you all know those symbols, 0 through 9. So for base 6, we would need 6 symbols. Because once, just like in 10, once we get up to the 10th thing, 0 is the first. That difference between ordinal and cardinal numbers. 0 is actually our first number. We can't do math with first and second. So once we get up to 10 things, we loop over to the next column. So same thing here. If we're basing everything off 6, by the time we get to 7, 7 will actually be in the next column. Because the biggest we could get would be 6 times 1. So we need 6 symbols. And we're still looking at numbers, so we'll use 0 through 5. I'm just going to make one up and break it down this way first. So 2, 4, 4 in base 6. So we have this 3-digit number, and we know it's in base 6. When we're doing multiple bases, it's common to write that as a little section after the number. So doing the same thing here, this means we have 2 times in the 0, 1, 2, 6 squared column, plus 4 in our 6th column, 6 to the first column, plus 4 in our 6 to the 0 column. Which anything raised to the 0th power is going to be 1. 6 to the first power is just 6, so we get 4 times 6. And 6 squared is 36. So we have 2 in our 36 column, 4 in our 6th column, and 4 in our 1's column. We just add those up to find the actual value of that. Which you can see, you can tell since I'm writing 6s, I've already jumped to writing base 10, the one we're familiar with. This is the only one in base 6. I guess I could write the little 10 down here so that we can make sense of what it is. Because 6 is not a symbol we have if we're using base 6. Our base is always written 1, 0. Because no matter what our base is, it's in the base to the first power with 0 ones after it. That's an important thing. So 2 times 36 is 72 plus 24 plus 4. What is that? 96, 100. So that is 244 in base 6 is how we would write the number 100 and that we're familiar with. Something called number theory. What these symbols represent, because they represent something real, 100 of something. We can use different symbols to write that. A standard example, well, I guess there's the famous one, the rose from the Shakespearean play, or the word dog versus the furry little things that we bend down and scratch the ears of. The symbolic representation is in many ways disconnected from the actual thing it's representing. Does the idea of a base there make sense? I know you know this one, but it's probably been a long time since you thought about that. But see how we could do that with any number we choose. Lots of useful ones, but in particular, we're here studying binary state machines. So there's a really good one. I'm going to write something up here before I erase this side. Base 10 is called decimal. There are fancy numbers for all of them based off the Greek names. You'll probably know a lot of them, but there's only a couple that we really need to worry about. I want to explicitly state that because that's going to make a difference when we get to the little, the fractional numbers, right? Because saying the decimal point doesn't make any sense if we're working at binary. And most people don't know the name of that. We'll talk about that in a second. So we're looking at studying binary state machines. So base 2 seems like it would be a pretty good base to use. Or binary, which just like base 10, we needed 10 symbols. In our pass through here, base 6, I just chose that arbitrarily. We need 6 symbols for base 6. So for base 2, we need 2 symbols. And we're still talking about numbers. So our first 2 numbers, 0 and 1, work out pretty nicely for it. And then we put our things together. I guess we could have gone backwards here. We start with 100, break that down. I'm gonna step back here to the intermediate one real quick. So let's say, oh, there's probably enough space. We started with 139, and we want to put it in base 6. That's in base 10. It's usually best to start with our largest column. 6 cubed is bigger than that, so I think 3 will be enough. If we divide 139 by 6 to 0, 6 to the first, 6 squared. If we divide 139 by 36, I'm doing the calculator, 139 divided by 36, we get 3 point something. So we would have 3 in that column. 36 times 3, and that covers 108 of that actual number. So then 139 minus 108, we still have 21 that we need to account for here. Our next column is the 6th column. So how many 6s will fit in 21? 3, right? Which would be 18. So we subtract 18, and there's still 3 more to account for. We're down to the 1s column, so just 3 there. So 139 that we're used to in base 10 would be written as 333 in base 6. So we can go both ways. We just divide, find out where the quotient is, and then the remainder carries over to the next column. Y'all probably haven't done a lot of that since elementary school, so that probably was just to review it. But we can do this with any of our numbers. So in binary, let me just make one up, 214 in base 10. We'll put that into binary. How would we represent that? So, well, there's a lot less symbols, so we need a lot more columns to do it. 2, 3, 4, 5, 6, 7, 8. Thought I heard the Zoom call beep, but I don't see anybody there, so maybe it was in another classroom or something. I'll zoom in on the board a little more. I just already knew that I was going to take 8 columns, but we know we're going to need a lot more for how many fit here. And again, our columns are set up the same way that we're used to in 10. Starting at the right, we have 2 to the 0, 2 to the first, 2 squared, 2 cubed, 2 to the 4th, 5th, 2 to the 6th, and 2 to the 7th, being our 8th column. Well, by that rule, anything to the 0 power is 1, 2 to the first power is 2, and then we just start doubling the numbers. But you probably already heard most of them because of our site is very reliant on computers these days, so these numbers show up a lot. 2, 4, 8, 16, 32, 64, 128. So I just went through and just doubled them each time. We have calculators, so you can punch in the calculator. Most calculators will do this. I usually keep this one for an example. So this is the scientific calculator from Dollar Tree, which I bought back when everything was $1 before it went to $1.25. And if you haven't seen it now, Dollar Trees have started selling other prices. So if you see something that seems like, it's like, why is that at a Dollar Tree? It could be a $5 or $20 item now. They no longer do that, everything's one price. It caught me by surprise. It's like, why is this $1? And then discovered it was a $5 item. But I paid $1 for this calculator, and then we'll do all these conversions right there in it. So yeah, we want to go through the process to make sure we understand how, but 214, so I'll put 214 in there, and then push second. And on this one, about the division says BIN. So when I hit that, it switches to binary. So that's the one we're getting to. So we have technology to do it, but we still want to go through the process, make sure we can understand it. So we're starting at base 10. So we'll kind of do this. We'll divide out each column, find the value for each column, and we get down there. So 128, how many times will it go into 214? And how many times is what we asked the last time? In binary, it's a step easier. Doing math in binary is not new. Egyptian scribes did math in binary. They took their number, translated it to binary because of that question I just pointed out. Back here, it was how many do we have? Or same thing here, if we're doing base 10, how many do we have? But we only have 2. One of our good binary state descriptions in English is yes or no. So instead of asking how many do we have, is do we have any? Do we have any 128s and 214? I see head nods. It's like, yes, we do. So then 214 minus 128. I'm going to write all this out. So 4 minus 8 is actually too big. We all probably know what that is, but we can borrow from the next column. Leave 0 from the next, from the 10, leave 0 and bring 10 over to this column. 14 minus 8, we can do that as 6. 0 minus 2, again, it's too big, so we can borrow from over here. We had 2. So we'll leave one of these behind and bring 10 over to this column. 10 minus 2 is 8, and 1 minus 1 10, but that borrowing, probably haven't seen that in a long time. So I wanted to remind you about that process when we get up to what the machine is actually doing. It's not really going to be a surprise when we build a circuit that does this. The machine's not going to skip steps like we do, and it's actually going to do every borrow and carry and all that stuff. It's simplified the way it actually does, but we'll see that coming up soon. So 86. Do we have any 64s in 86? Yes, we do. So minus 64 leaves us 22. Do we have any 32s in 22? Nope. I see heads shaking the correct direction here in the classroom. I assume the same thing on the Zoom call. Nobody's really shouting out answers. Will 16 fit inside of 22? That would have been the question that like ancient Egyptian scribes asked. Will it fit? And it's yes or no. 22 minus 16 leaves us 6. Oh, I should borrow. We do all the borrowing and that column, the columns operations have 6 behind. So yes, we had a 16. 8s. Will 8 fit inside of a 6? Oh, no 8s. 4 will fit. Okay. Minus 4. We've got 2 left to account for. That's our next column. So yes, that'll fit. And we don't have anything left to account for. So the rest of them are going to be zeros. So 110101110 is how we would represent 214 in binary. Does that make sense to everybody? See how it's something you already knew? Just might not have seen it written out if it's the first time you've seen it. Let's go the other way. So let's start with 1. I'll do a 0 first. 0, 1, 1, 0, 1, 1, 0, 1. We have this number in base 2, and we want to know what that represents because we live in a world where we use base 10 for everything. What did you use back home? Did you use base 10, Mom, before moving to America? Most countries in the world use base 10, right? Yeah, humans have 10 fingers, so this is convenient for us. I'm pretty sure everybody in the world uses base 10. There might be a couple that use 20s, base 20, because we have toes too. But we don't use base 2. Actually, the biggest problem with this is it's too simple for the human mind. We'll get to it in a moment, but when we go to work with it, we actually make it more complicated because we can deal with more than just the 1s and 0s like the computer. So we add extra complications if we're actually going to work in binary. So we can just start with our columns and do the same thing we did here, back to the meaning. So we 1, 2, 3, 4, 5, 6, 7, 8. I'm probably going to spread that out a little more, but we have 2 to the 0, so we have a 1 column. I'll write it like this, then a 2 column, and then we just keep doubling them. 4, 8, 16, 32, 64, and 128. Each particular digit is called a bit, for binary digit. Just combine those 2 words and then do away most of the letters. When they first were starting building computers, they were doing that 8 at a time. So then a byte is 8 bits. Then we get into words and pages, and those are a little bit different. A word is probably 4 bytes, and a page varies depending on the size of your register. Eventually, we went up to the one that's, so in 2023 in America, it's probably 64 bits, unless you have a computer that's several years old. But most of the 32-bit stuff is kind of faded into the past. So our pages are 64 bits, and a word somewhere in between. which lately, since we have 64-bit pages, 2 words to a page or 4 words to a page. So you're going to see 16 or 32 bits there, but most people don't talk about words and pages quite so much. Pages show up if you get digging into operating systems, but back to just our simple 1-byte number. We'll do the same thing we did here. And again, we have that simplification because we have 0 128s. I'll write it all out this time. Plus 164. Actually, that's probably enough. So if we multiply by 0 by something, what happens? It's gone, right? So we don't really need that. And we're back to that yes or no thing. No, we don't have any 128s. And we don't, if we multiply by 1, it doesn't change anything. That's our identity, our multiplicative identity. So we can just say, yes, we have a 64, and then it cuts out that multiplying by the column state because it's back to that yes or no question. So yes, we have a 64. Yes, we have a 32. No, don't have any 16s. Yes, we have an 8. Yes, we have a 4. No 2s. And yes, we have a 1. So we would just add those numbers together. 96, 104, 108, 109. Does that sound right? Somebody want to check my math? If anybody's got a calculator on hand. So that's how we would write 109 in binary. Does that make sense? There's nothing, you've seen the pattern before. It's a lot of 1s and 0s to write down. Let me do a couple short ones. 1001. Somebody want to tell me what that number is? Shout out the number 1001.
Is it 9?
Yes. 0110. Somebody else want to say that one? Whatever column number is written down here.
6.
Yes. That one. Somebody else can probably tell me that one.
5.
You see how we get to that number now, right? Instead of that arbitrary pattern of switches. And the 1s and 0s are a lot quicker to draw than this wiring schematic, electrical schematic. But it looks like that's kind of making sense how we get those numbers. But we do more than just write our numbers down, right? Like this. The subtraction, or addition, and multiplication, and all those other operations. It's okay if I erase this side? We've moved on from base 10, and then that base 6 was just passing. Oh, I guess I'll show it real quick. The fractions are kind of follow suit. 3.14. Here we have 10 to the 0 column, 10 to the first, and so on, the way we would normally write that number. Then over here, our first column is 1 over 10. Then 1 over 100, which the 100 is 10 squared, and the 10 is obviously 10 to the first power again. If you haven't seen it in math class, another notation we have that we can use is if our exponent is negative, that really means we're on the wrong side of the fraction bar. So instead of 1 over 10 to the first power, we can just write 10 to the negative 1. 10 to the negative 2, and so on. And the little dot there is called the mantissa. Nobody ever uses that word. Floating point might be, might say floating point, because that applies to any of them. It's not called the decimal because if we wanted this in binary, we could put a little dot to separate whole number and fractional parts and binary just the same, right? Our ones column and our twos column make a 3. And instead of basing it off 10, it's based off twos. So 2 to the negative 1, 2 to the negative 2, 2 to the negative 3. And I'll kind of stop there because it's still interactive. I'll start writing pi, it's still an irrational number. We could write digits of pi forever, no matter what base we're using. An irrational number is still an irrational number. Sometimes we'll get strange things. A common question you'll see in programming uses the state X in Indiana because 1.07 in base 10 does not come out nicely in base 2. When we go to translate it, we keep adding columns, and computers have a finite number of columns. 64 columns for the base 2 fractional part is not enough to represent 1.07. So you'll kind of see that somewhere, and it gets rounded wrong and truncated at the wrong spot. But 2 to the negative 1 is 1/2. I'll write the decimal numbers we're familiar with: 0.5, 0.25, 0.125. So then we're back to that yes or no question. So we need to count for 0.14. Our first column is 1/2, the halves column, so 0.5 is too big. So we don't have any of those. Next column's quarters. 0.25 is still too big, so we don't have any of those. Eighths would fit, so we would have one of those, and then 0.14 minus 0.125 again leaves us, oh, there's a 1. 0.015, so we would just keep going. Half of this would be 0.0625. Which would be too big, so we get another 0 and just keep going until we find those other digits. But it follows the same pattern we know. Nothing new there. But we would also add and subtract things. Let me do a couple here. So maybe we have a 13 plus a 15. Actually, let me do something we can add and subtract. Put all of them on the same example. A 13 and a 7. Don't need quite as many bits to write that. Back in base 10, way back in elementary school, we're adding these. We do it column by column. 3 plus 7 is 10, which our base is already written 1, 0. So 10 in base 10 is 1, 0, which means the 0 goes there, and we carry the 1 to the other column, and then we add that down. 13 minus 7. 3 minus 7 is too big, so we actually need to borrow from that other column, and then we get 10 plus what we had there, so 10 plus 3 gives us 13 minus 7. We get a 6. No surprises there. But if we're going to use this numerical system, it better follow the same pattern, right? We better get the same thing if we try to add these numbers. Anybody want to try to tell me how to write 13 in binary? 4 bits will work. 8, 4, 2, 1. Which of those columns do we need to add up in order to add those columns to add to 13?
31101.
This is a really easy system. It's easier than the system we're familiar with. It follows the same patterns. Or actually, this one was to prove that it follows the same patterns. And we want to add to a 7. It's a nice little trick with 7. 7 is 1 less than a power of 2, right? 8's a power of 2, so if we had an 8, it'd be 1 followed by 3 zeros. 1 less than that is a 0 followed by 3 1s. Because if we add 1 to it, that carry is going to keep happening until we get zeros in all those first three columns, and it goes right over. So 1 less than a power of 2 is going to be all ones with the 0 up front. Then we can add these. What's 1 plus 1? And in binary, how do we write 2? Yes, which takes 2 columns. So a 0 in this column, and we carry a 1 over here. And again, we're back to 1 plus 1. 2, so 0, carry a 1. And 1 plus 1 plus 1. Okay. See how the math is pretty easy here? How do we write 3 in binary? 1, and we carry a 1. And then 2, and then I don't have the column there, so I'll just write it down there. 1, 2, 4, 8, 16. So 16 plus 4 gives us 20. See, that's a little bit easier because this is the biggest we'll get. There's a restriction you probably didn't see in elementary school. You never want to add more than your base. So if you're going to add in base 10, if you were going to add 15 numbers together, you would want to add the first, no more than the first 10, and the result of that, add the other 5. Otherwise, you'll be carrying things multiple columns over. You have to carry too many columns over, and then the next a column in between might carry to another column in between, and that carry spot gets off if you do that. So with binary, probably never showed up because if you were looking at adding 12 numbers together, you probably broke it down and did it in little chunks anyway, just because that made a big, huge list that looked overwhelming. But in binary, that does show up because we never want to add more than 2 numbers together at once. We have a bunch of numbers, we need to do it in separate stages. And yeah, because things would carry too far over. If we had 1 plus 1 plus 1 plus 1, we get a 4, and that carries 2 columns over. So our carry bit's in the wrong spot for where we're getting ready to work next. It's a restriction that you probably never encountered earlier. Well, same numbers here, 1, 1, 0, 1, and 0, 1, 1, 1. And this time we're subtracting. How much is 1 minus 1? Zero minus 1. We know that would be -1, but let's go through our pattern here. Just like we did here, 0 is smaller than 1. So to follow the pattern, we really need to borrow from the next column over. There's a 0 there, and we borrow 1, 0, which is a 2. So now we have 2 minus 1. That's the one that those people off at first when they bring that over. 2 minus 1 is 1. Same thing here. We need to borrow. 2 minus 1 leaves us 1, and 0 minus 0 leaves us 0. 8, 4 plus 2 is 6. No zeros, so we still get the same thing when we do all of our math. So all of that stuff that we do with our numbers is separate from our representation of the numbers. Works no matter what base we're using. Here, we kind of saw, y'all probably all wanted to put a negative number there. We need to talk about negative numbers next, but it's probably a good time for a break. Seems like a good pause point, right? Does 10 minutes sound good to everybody? Because we've seen the math, so now we need to get into where we build that math into all of our systems. We want to build from one simple operation to get everything, right? Multiplication is repeated addition. Division is repeated subtraction. Exponents. We want to build it all from one system. So that's what's next. And we need negative numbers in order to do that. So my laptop says 202. 10 minutes sound good. I see head nods. So we will get back to it at 212 and start looking at negative numbers. And the 0 problem. That actually causes a big problem. We'll look at the issue with just negative numbers. See, I'm